best ones I've drawn. Okay guys, in this one, still going on the wave behavioral light, we're going to start talking about waves that are in phase and out of phase, what incandescent light sources actually are and why they're not coherent or monochromatic, and then rehashing a little bit of interference of light using the principle of superposition. Alright, so to start with, the phase of a wave is determined by where it actually is in its cycle, so whether it's the peak or the trough or somewhere kind of in the middle. And for waves to be in phase kind of means that they have to be doing the same sort of thing at the same sort of time. So we have waves like this. If these two waves were going to meet at a point here, they would probably arrive at that spot in phase. Okay. In order to be out of phase, one of these would be completely 90 degrees out of phase with the other one. So it'd be doing the opposite. So peak here, trough here. So these would arrive out of phase. So in order to be considered coherent, wave sources need to maintain a constant phase relationship. So coherent, a constant phase relationship. So it doesn't mean that they have to be in phase or out of phase, they just have to be the same amount in or out of phase all of the time. So this light source here is going to result in destructive interference, but at the moment they are still able to maintain a constant phase relationship. So if they were the same wavelength, they're both the same colour blue, so they would continue to oscillate at whatever it is, 450 nanometers, give or take, 460 nanometers. So that's not an oscillation, that's a wavelength. They will continue on with that sort of wavelength all the time. So taking the same size steps, they'll be moving at the same speed, they'll have the same frequency, so they'll remain the same amount in phase or out of phase all of the time. So they're able to maintain a constant phase relationship. That's kind of important terminology. If there's something in the exam or the test that talks about coherent sources, that's a phrase that you need to be able to understand and write down, I guess, and unpack it a little bit. Monochromatic is mono, meaning one, chromatic, chrome, colour. So monochromatic light is one colour. So these two things here can be considered to be coherent at the moment because they're able to maintain a constant phase relationship and they are the same colour. An incandescent light source, though, is one that is made up of a filament. Let me do this. Let's go a light globe with a filament in it. So an incandescent light, that's not the best one I've drawn, which doesn't say much. An incandescent source is one that glows because the wire is hot, or glows because it's heated. So you get an oxytorch on a piece of steel and heat it up. Some of the particles, the charges that are vibrating around in there are going to vibrate fast enough to be able to give off visible light. In an incandescent light source, you turn the light switch on and something moves fast enough that charged particles in the filament itself vibrate backwards and forwards fast enough to be able to give off visible light. Because there's a range of temperatures that those charges in that filament are going to be able to vibrate, we end up with white light being made up of a mix of, I'm going to call that red, green and blue. So stuff vibrates at different frequencies depending on how hot or cold it is. So the hotter it is, the more blue it is. The cooler it is, the more red it is. So you'll notice when you heat up metal with an oxytorch, it starts off kind of being this dull red colour. If you were to touch it, you'd burn yourself because it's got a lot of particles that are in there that are vibrating nice and fast, but they're only able to give off infrared radiation, so heat. But you get some of them are starting to kind of be a dull red. As you heat it up a bit more, you've got some that are dull red, some that are red, some that are now fast enough to be going orangey yellow colours. And now the piece of metal kind of looks like a reddish orange. As you continue to add more and more and more heat, some of the charges in there are able to glow faster and faster. So they're able to give off faster and faster colours, or higher frequency, higher energy colours. So you end up with this kind of idea in a filament in a light globe. So you end up with Roy G. Biv, so all of the colours of the rainbow. What that means is that because all of these colours have different wavelengths, so you'll see the red one is longer than the green is longer than the blue, because they're not able to, because they're all different colours, they're all different frequencies, they've got different wavelengths, they're not able to maintain a constant phase relationship, simply because even though they could be in phase or out of phase at any given point, they're not able to maintain that relationship. So you can see, at a point, so right at the start here, so there's a peak, there's a peak, there's a peak. They're somewhat in phase at that point. But if we go a little bit further on, that's a trough, that's a peak, and that's a, God knows what that is. They're not able to maintain that constant phase relationship all the way through. So therefore they cannot be coherent. The other thing is they're obviously different colours, so they're definitely not monochromatic. Now, when you have, I'll go blue again, when you have a coherent and monochromatic light source, so something like the sodium vapor lamp is considered to be coherent, even though that's, not worry about the fact that there's actually a few other colours in there. 99 point something or other % of the light is the yellows. There's two of them that are so close together they're pretty much the same colour. A laser beam, for instance, is a coherent monochromatic source of light. We're able to use the wave behaviour to do interference patterns. So over here I've got two waves that are going to meet at the same point at the same time, and we're going to use the principle of superposition. So superposition means, remember, fancy word for vector addition, or adding one vector on top of another, same as vector addition. So if we have a peak and a peak, a trough and a trough, and we're going to add all these things together, so if we add that together, we're kind of going to get something that's the same wavelength, but it's going to be double the amplitude. So we're going to add this amplitude and this amplitude together. So we're probably going to end up with something better drawn, but you can kind of see the idea. Here, if we add these two together, we're going to have a peak on a trough and a trough on a peak. These are actually going to cancel out and we're going to get absolutely nothing. So when waves arrive perfectly in phase like this, we're going to get perfect constructive interference. When they arrive perfectly out of phase, we're going to get perfect destructive interference. All right, and that's all because they are, if they're coherent, you can actually do this. If they're monochromatic, you can actually do this with laser pointers. With normal white light, you don't get this pattern, which is why we don't have bright and dark spots in the classrooms. Yeah, thank you.